when you do calculations with measured quantities, it's nice to be able to know, well, what's the uncertainty on my new figure? One way of taking care of that is to use significant figures. And that gives you basically the number of reliably known digits in a number, and you can use some rules for figuring out what significant figures you start with and then how to propagate them. So here are the rules for significant digits. Anything that's not a zero is significant. Any zeros between significant figures are significant. So 120.3, well, the zero is between the 1, 2, and the 3. The 1, 2, and 3 are all non-zero, so they're all significant. So this has 4 significant figures in it. Anything that's greater than 1, for numbers that are greater than 1, any trailing zeros are not significant. And the reason why is because they're just telling you how big the number is. They're not giving you actual precision in that measurement. So here, 120, you don't know that this zero matters or not. So by default, it doesn't matter. Anything less than 0, again, the leading zeros just tell you how big or small something is. They don't tell you the precision on the measurement. And so you would have 0.034 being only 2 significant figures. Any decimal places that are with trailing zeros after them, or here at the end, tell you that these zeros are actually significant, because that's the only reason we're writing the zeros, is to let you know that actually I know these are zeros here. This is also one of the reasons why using scientific notation is useful. I'll talk about that in just a second. So basically, you keep your extra digit during calculation and you round the final result to the number of significant figures as indicated by these following rules. So when propagating significant figures, when you multiply or divide numbers, the result should have the same number of significant figures as the fewest number going in. It's easier to see with an example. 11.3 centimeters by 6.8 centimeters gives you 76.84 centimeters squared, right? So that's just the multiplication. That's what we get. And when we look at the significant figures here, we see that we have 3 significant figures and 2 significant figures. And what that means is between 3 and 2, 2 is the least number. So this result, which has 4, we round to 2. So you round to 2 figures, which means that the smaller things get rounded off. The 6.8 rounds up to a 7, and so we end up with 77 square centimeters. When you add or subtract, then your answer can't be more accurate than the least accurate number used. And you can think about this like, I've got a mile plus a centimeter. Well, that's really just a mile, right? Like, since I don't have the mile accurate to within a centimeter, it's just a mile. And so the same idea here, 12.34 centimeters plus 5 centimeters. Well, here there are 4 significant figures. Here there's only 1. But what you want to do is you want to look not at the total number, but at the digits that they're in. So here this is in the ones place. My 5 doesn't have anything after the decimals. So this has numbers after the decimals. Here we use no more accurate than the least accurate number. This least accurate number rounds off at the ones digit. So here we round this off at the ones digit here. Because you don't really know this 5 being any, like this, the idea is that in any of these numbers, there's uncertainty in the last digit. So this 5 could be plus or minus maybe 1, right? Maybe plus or minus a half a centimeter. But either way, like you don't know when you add on the 0.34 here that you're actually ending up with 17.34. So you round those off and you're left with 17 centimeters. When you plug stuff into your calculators, it doesn't give you the right number of significant figures. And we noted that some of the trailing zeros can be confusing for things that are above 1. So here, scientific notation helps. 4,300 meters is unclear. Do I know it as 4,300 exactly? Or do I know it as 4,030, but then uncertainty is in here? Or is uncertainty here? Like, at what point am I uncertain about the numbers? To make that clear, we can write this as 4.30 times 10 to the third, and this makes it clear my uncertainty is in this last digit here, right? So we include the digit where our uncertainty is in, and now it's clear. There are 3 significant figures. Now I might get myself in trouble with this opinion that I'll give in just a minute, but my preference is I don't really use significant figures a lot because I find that in cases where I care about the uncertainty, I want to be a little bit more rigorous than this. And in the cases where I'm just doing ballpark figure calculations, a lot of engineering calculations type stuff, you generally round to 3 or 4 digits anyway, and know that you don't really know anything better than that, and try and make sure that most of the things going in are in that same ballpark. And so if you're getting within 5% of the actual value you're expecting, that's pretty good for a lot of things that I do. So anyway, if I need to be more precise, I use different techniques. But let's go ahead and do an example and see if we can follow these rules. 2.345 times 10 to the second meters. We want to multiply it by 0.0023 meters and take into account significant figures. All right, so we take the 2.345 times 10 to the second meters, and we multiply that by 0.0023, and we get a number. So this is just whatever number we get, we plug this in, we get a number. The units, this was meters, this was also meters. I left off the meters here. So we end up with units of meter squared. So now, what are the digits? Well, here we have 4 significant digits. Here we have 2 significant digits. These are all leading zeros that just tell us how small our number is. And so we round to the least number here, which gives us approximately 0.54 square meters. So that's the calculation and then rounded to the correct number of significant figures. So again, my preference is I generally just round to 3 significant figures anytime I'm presenting results. You don't ever want to present something like this unless you know for sure that I have some idea about what these values in these trailing numbers are, because it gives the impression that you do. But if I round it to like 0.54 or 0.539, like that puts me in the ballpark of probably about how well I know this anyway. In this case, one of the inputs is not as good, and so we actually don't know it that well. But that's that. That's how we use significant figures to communicate when I tell somebody the answer here that I don't actually know it this precisely. I only know it maybe precise to this digit.